Welcome back to Bionics of Surfaces. Today we're going to be looking at this website, but first of all I should apologise for my eyes being particularly weird. I'm using a green screen and it's detecting one of my eyes as the same colour as the screen, and so it's quite freaky. You can see the text through my eye, through this one here. But anyway, we'll have to live with that. I can't fix it at the moment. So we're looking on this website. This is the address up here, so you can use that yourself. And the first bit that I'm interested in, or the first page that we will look at, is this one, I think. No, let's go back to the index so that you can see where everything is. And this is the first page, thermodynamics and chemical equilibrium. This is our topic, and you can see useful things over here disappearing behind my head. I'm going to move the top down so you can't see the headline, which allows me to show you a little bit more of the screen. Just get it the right size so that it fits on. So this first one we're interested in, this first section here, energy spreading, driving spontaneous change. That's what we're going to do now. So to get there, you have to click on it to go to this page, and it shows that well, it gives an example where T in this case is spreading inside a liquid, and it doesn't go backwards. We observe that as not going backwards, and we would have up to this point said it's due to the increase in randomness in the system, but we should really be careful and do this properly. So if we look at this, a spontaneous process, so we first of all have to define what we're talking about. They're defining it here and saying a spontaneous process is one that happens on its own, and if it isn't spontaneous, then you have to do something else to get it to happen, or you have to go a different way round. So if we go down here, there's a lot of explanation in here, but this is an example of coins and throwing in coins. Normally, so this is the sort of bad bedroom example where you start off with ordered coins and randomize them, and it is unlikely for them to go back to their ordered state. So in this case they omit the fact that it starts off with all the coins one way up, and then you throw them randomly and they land in some kind of mixed state. Or in this case, the second one, you take two identical pieces of metal and you put them in contact. They start off at different temperatures, so the average temperature doesn't change, or the total energy doesn't change, but it spreads between the two, and it doesn't go in reverse, which is one of the laws of thermodynamics. We already had that one. Effectively defining entropy. It's freaking me out as well. Sorry about that. Now here we are. We take something and we drop it. Effectively we're turning kinetic energy into heat at the end, but we need to go up back in time before that. We start off with gravitational potential energy that we put there somehow by lifting it, and then it's converted into kinetic energy, and then it's converted into heat and sound, and eventually into only heat. And we would like to explain why these things are spontaneous, why they happen, and why other things don't. So why the book doesn't gather heat from the room, cooling our room down, and then shoot up in the air. We know that doesn't happen, but we should explain why. And diffusion is a classical example of a non-reversible process. It's one of the very few that are reasonably perfect. So if we have something, we allow it to expand, in this case a gas to expand, then it always increases in entropy because the particles have more space to move around in, But why? Because there aren't a different number of particles. They're not hotter. In fact, they probably cool down. So let's see this. So here's this direction through disorder statement, where they say, if we increase the amount of disorder, we have defined the direction, which is our entropy that we've had up till now. That's not entirely the best explanation of entropy, so we will look further down in this page to see what's going on. But here is where they are gradually transferring from an order-disorder sort of visual representation to a more correct representation. So if we look at this, we see that some of the heads are, some of the coins are one way up, some of the coins are the other way up, but each one is only one direction. And if we take this and draw it as a table of possibilities, it goes behind my head, sorry, but we can have either, so we only take four, either naught heads or four heads, and there's only one way those can happen, or we can have one head and there's four ways that can happen, or one tail and there's four ways that can happen, or two of each, and there are 6 ways that can happen. So the probability that we end up in a mixed state is way higher than the probability that we end up in either of the other states. You'll have done this in maths. Effectively, it is much more likely at random to end up with a mixed state than it is with a pure direction of one or the other, even though they're all equally likely. So now we're going to the more interesting bit, to the spreading of energy. So this is more important because it's more the real result that we want to talk about. So if we take if we take some molecules and we put them in a box for some reason, then they can be in different states, and the energy that they have can be put into different ways of, now it can be stored in different ways. So the simplest way that a molecule can store energy is translation. It can be moving faster. The next simplest is rotation, and then it can be vibrating. And then it can be in electronic excited states, so the bonds can be excited too. If we look at that, we can see this. I'm trying to get to the nice one. Yeah, that's an example. So if we look at this particular one, we can see, so here we've got translation, that's movement, and they are very, very close together. So if we've got this much available energy, then we can have any translational state in this bar. It could go faster. Then we've got possible, this is weird, but anyway, vibrational states that it can have. And in this case, they've got the second most, or the second least energy gap, the second most common. And so we can fill only 1, 2, 3, 4 of those states, or probably this 5th one, if we use up most of the energy. So we could fill 4 of those states. And in rotation, there are only 3 in there because they're further apart in this particular example. Typically, rotation is the second one. So if we want to divide the energy that a molecule has, it will have some translation, it might have some vibration, and less likely it'll have some rotation. But on average, between all of the molecules in the box, some of them will have more of rotation energy. They'll have put their energy into rotational energy. Some of them will have put it into translational energy. And when they hit each other, they will swap over. If we measure temperature, remember, we will only detect the translational energy, and that means, consequently, if they actually decide what they're going to do, so if all of them suddenly picked up a lot of rotational energy, they would actually get cold. If they all converted all of their vibration and rotation into translational energy, they would get hot. But in reality, on average, the amount in each stays pretty much the same. So some of the energy is here, some of it's here, and some of it's here. The energy is spread out, and the more the energy is spread out, the higher the entropy. So if we imagine we cool the system down, as we cool it down, this yellow band gets smaller, and if we get down below this level here, which I'm showing with my mouse, I can see that. If we get down below this level here, we cannot have any rotationally excited molecules anymore because we haven't got enough energy to excite one. So if we get below that, we don't really have enough energy to do that. It's not strictly true because we can take energy from several molecules and put it into one. So we could jump up, but on average there will be very few excited in the rotational levels, and most of them will be just translationally excited with a few vibrationally excited. And if we cool it down below here, then we can turn off effectively the vibrations as well. So the hotter it is, the more possibilities the system has, because we can have more and more different potential energy states, and the probabilities or the possibilities get bigger, and that we can sort of see to a certain extent, go back up, is similar to this with the tossing coins, but it's in energies and how spread out the energies are in possible energy levels, which is more correct. So the next part on this page says the same thing again, actually. So if you look at it, it says it again. If you find it easier to understand that way around, that's better. Ooh, weird. Anyway, so this says the same another way around. It's effectively the same as the coin example, but in molecules, and they've got different molecular states, and then saying that the more possible states that we have to share our energy around, the better it is. And then it goes on to explain why, in this case, okay, let's have a look at this one, dropping the book. Effectively, we're spreading the energy around because the energy starts off only as gravitational potential energy. So nothing new has happened. When you let go of it, it converts into kinetic energy, and that is because there is a force on the book from gravity, but the quantum mechanics or the thermodynamics comes in when it hits the ground, because then the energy is spread out over many microstates, over many possibilities in the room, because we've heated up a whole load of things. And that's what it's trying to say. So the problem there is obviously this theoretical heat death of the universe where everything's spread out, so everything becomes really boring. So then we have this other question about gases expanding, which is also linked to things spreading out and mixing, but it's somewhat more fundamental. So what we're doing here, as they explain in this piece of text, as the gas expands and it expands, because there are more possibilities for the molecules to take kinetic energy, then there are more and more potential microstates, because effectively the states, here we are, oh, it's behind my head, let me move it up. There it is. So A and B, so if we have state A where we've got them all on one side, then we've got all of these potential states that we can have in here. If we have B where they're allowed to go into both sides, then there are more potential states because they can be in more positions. So then we can have more ways of distributing the energy, which is drawn on this diagram, or manifests itself in this diagram as the energy states being closer together. So in effect, spreading it out, which doesn't change the number, it doesn't change the number of configurations, but it does change their exact position number of configurations, and it also changes the energy states, the number of energy states that they can be in the same condition. Obviously, there isn't a limit to the, or there isn't necessarily a limit to the number of energy states that they can be in, because we could heat it up. Oops, sorry, I'm pointing with my finger. Because we could heat it up, there's my mouse, a bit above this point, and we would get the same number of states, obviously, back. But in the larger box, the energy states are closer together, which means that we can have more for the same heat. Then we got, why does heat flow from hot to cold? Again, it's because the total number of possibilities of energy states goes up, and that is in this case because of the way that the energy gaps change. They're not linear as they are in here. They're not the same. Every step isn't the same. They get further and further apart. And so in this case, having a larger warm, or having two warm objects, we get more potential energy states because we get more, we're increasing them quicker at the bottom than at the top, so we get more. This is also a reason, by the way, this is also a reason why it's really hard to cool things down to absolute zero, because the gaps between the energy levels get closer and closer and closer together, so it's hard to get down there. Because we're confining the particles in there, or the system, to less and less states, and that is more and more difficult.